I just wanted to go over quickly on the logistic regression. Since our dependent variable is nominal or categorical in our case, which is a nominal categorical, which is high dot quality. It's either 0 or 1. And we can't do a simple linear regression, but we can do a logistic regression. And I just wanted to show you what that looks like, and then I'll quickly run it. I don't know if you guys want to use this or not. Since we didn't have any time, I decided that I'll just record a video and hopefully have you watch it. So when you run a logistic regression, what we can do from the regression result is we can calculate the probability that our dependent variable is 0 or 1. So the p here, the p that you can see right here, is the probability that our dependent variable would be 1, right? And this is how you would calculate it. So if we had one independent variable, age, and the beta that we get is beta 1, and then beta 0 is our intercept. And if we plugged in everything, we could get the y, and we could transform y to p by using this formula. P equals e to the power of y divided by e to the power of y plus 1. I'm not going to get into why it's done this way, but it's very simple to calculate. I just wanted to give you the intuition, but then I'm going to actually show you something when we run the regressions. So for now, I'm just going to run a simple version of it. Actually, I chose it wrong. We want to do just fit y by x, and I am going to choose, I could choose one of the variables, but I'm going to choose all of the independent variables as our y's, and we can have by category. Oops, I made a mistake. Our y should be our nominal variable, which is the high dot quality, and our x's will be our explanatory variables. Go here and we can click run. So this gave us a bunch of stuff, but don't panic. There's actually a pretty nice intuition behind it. So this 0 to 1 is the probability that the given observation belongs to high quality 1. In other words, the wine is high quality. So if we go, I'm going to ignore this one because it looks weird. I'll go to volatile.acidity. You can see that if the volatile.acidity is around, if it's around 0.4, for example, right here, if it's a little bit over 0.4, then we have a 50% chance that the wine belongs to high quality. So if you go somewhere like 0.8, there is a very, very high likelihood, almost close to 1% that the wine is high quality. And you can see that the p-value shows us that this is significant. Some of them are not significant. So this is, for example, not significant, and this is for the red wine, and we get different results for red and white. Again, so for red wine, this variable citric.acid is also significant. We can see that there's a negative relationship between citric acid. So the less you have, the higher the probability that the wine is going to be high quality. And we can see again at 50% probability that puts us at about close to 0.6 for this citric.acid variable. And if we have less than that, then the odds are more than 50% that the wine is high quality. So I just thought this was interesting. You can see that we have results for the white wines as well. here we are doing it one variable at a time. So this is fit y by x. We could choose to fit the entire, so use all the variables as we do with multivariable regression. However, the problem there is that I get bad results. I get poor results. I think this is just a guess. I think it's because our sample size for, I think it's for the, if I'm not mistaken, it's for the red wines, right? Yes, so our observations for the red wine is pretty low. We have 81 total observations, and I don't think that's enough for this many variables, explanatory variables, but I'll just show you what we get. Now I must say, when I run this, what I'm about to run for all the wines, and just looking at is it high quality or is it not high quality, so anything from mediocre to below that, a lot of the variables are actually significant, but when we run it like this, you're going to see that a lot of, I think for red wine, none of the variables will be significant statistically. So if we choose these as our x's, and if we have high that quality for our y, and we go by category. So when I run this, you can see that for the red wine, nothing is significant, and for the white wine, I think this is the white wine. Let's make sure that it is, yes. So this is white wine. Then some of them are significant. So let me make that larger for you. I can't, unfortunately. So volatile that acidity is significant, residual that sugar is significant, and so on. But my point is, for example, here on red wine, none of the variables are significant, but when we don't control for the other variables, when we do it one variable at a time, we can see that a lot of the variables, for example, here for red wine, a lot of them are significant. I don't know if you guys, what do you guys think of this? But I just thought it would be, this is interesting. I don't know if it's useful for us, but it's pretty cool that it gives us a probability, especially the graphs show us that show us the probability that a wine would be considered high quality or not. Simple exercise here. Let's choose a point and see what that point gives us. This is one of our observations, for example. I just chose this randomly. Now, not randomly, I wanted to have something that was obviously high quality. Now we can see that based on the density, variable, this point would fall on the graph at, I would say, around, let's say, 80–90% probability that it's high quality, the wine. Using the pH variable, we can see that the observation would fall on the graph at here, which is clearly above 50%, let's say 60% or 60-something% likelihood that it's high quality. I'm looking for a contradiction. Oh, here we can see that there's a contradiction here. So this point, this observation would give us an alcohol value that would fall on the graph here, and that would give us less than 25% likelihood that the observation is high quality. So here we are getting a contradictory result. So it's important to note that for any given observation there is error. And I'm not sure whether we have to do this we have to run this analysis by controlling for all the variables. In other words, using all the variables in one regression, or if it's okay for us to do it one by one at a time, fit y by 1x at a time, which is what we're doing here. And again, if we look at the same observation, if it falls on the line at this point for citric acid, and it will still give us roughly around 60% likelihood that the observation is high quality. So more than likely, so more than 50%. All right. Thank you for listening.